Okay, in Chapter 13, we're going to be talking about solutions. So remember, solutions are is synonymous with homogeneous mixture. In solutions, we have components, which is what makes up our mixture, and basically, solutes are minor components, and they can be solids, liquids, or gases, and you can definitely have more than one solute in a solution. Okay? When we talk about solvent, that's the major component. So, and that determines the phase of solution. So in other words, for example, here in pewter, it's tin, antimony, copper, bismuth, sometimes silver. And tin, being 85 to 95%, is going to be my solvent. And these are 2%, between 8%, 2%, smaller than that. So these are all my solutes, okay? And since tin is a solid, pewter is a solid. If we look at seltzer water, which is just carbonated water, it's water and carbon dioxide. Carbon dioxide, in this case, is a gas solute. But when you look at seltzer water, okay, you don't normally see the carbon dioxide, okay? So it's dissolved in the water, makes a solution, but the phase of my seltzer water, my solution, is defined by my solvent, which is water. Now, if you say, well, when I open the bottle, I start seeing bubbles, we'll talk about equilibrium in Chapter 15. Once you open that bottle, it's no longer an equilibrium situation. So the carbon dioxide gas, there's too much in the water and will come out. But before you open it, if you look at a bottle of seltzer water, you won't see the bubbles because basically it is in equilibrium and you don't see the gas. It's dissolved all in the water. Air, which is 78% nitrogen, a little over 21% oxygen, the small, less than 1% water vapor, carbon dioxide, etc. This is my solvent, and these are all my solutes. Okay, so these are just examples of different solutions. Okay, what we're going to talk about when we do talk about solutions, we are going to focus on aqueous solutions. So we're going to focus on aqueous solutions. Okay, so our solvent is going to be water. And before we talk about concentration, let's talk a little bit about mixing and the solvation process. So there is what we call a tendency towards mixing. Okay, and if you have a chamber that has oxygen here and nitrogen there, and then we remove the wall, the oxygen doesn't just stay here, but my oxygen gets distributed throughout the whole, let me give it space so you know it's a different molecule, gets distributed through your whole container. And this is, why is this? When you do that, you want to maximize your entropy, the randomness. Okay, so this is nice and orderly. I have oxygen on one side and nitrogen on the other, whereas here it's all mixed up. So this, when we say we have a tendency towards mixing, we have a tendency towards maximizing the distribution of everything throughout my container. And in a sense, you can see that as well. Suppose you had this is water, okay, and this is, let's say, concentrated punch. Okay, when you carefully combine the two, Or let me just, you're going to want to mix it and drink it. So let's just say, how about red food dye? Okay. You can, in your water, just carefully drop the red food dye in there. Okay. When you do that, over time, what will happen is the water will turn a very light red. And the reason it does this is because here, like I have oxygen and nitrogen separate, I have water and I have my red dye. And all we're doing is letting it mix over time. It's going to mix and it's going to distribute everywhere. So it's maximizing your distribution. You're maximizing your entropy. And this is what we talk about when we talk about the tendency to mix. Okay, let's continue. So what we're going to talk about now is the intermolecular forces in mixing. We already talked about what a solution is, some examples, and we talked about the natural tendency towards mixing, that we want to increase our entropy and randomness. Now, what are the forces involved in mixing? And we already discussed in chapter 11 the intermolecular forces. So we have London dispersion forces that we talked about, dipole-dipole, and the hydrogen bonding. And we also talked a little bit about ion dipole, and we'll see that in the solution, okay? But we also don't forget in the solid, when we look at solutes, if they're solids, we have the ion-ion bonding, okay? So this is basically bonding, because we're actually breaking up those bonds when we dissolve ionic compounds in solution, but in molecular compounds, those covalent bonds never break. They're very strong. Okay, so what we have to consider are solute-solute interactions, solvent-solvent interactions, and solute-solvent interactions. And what we need to bear in mind is that when I look at my solute-solvent interactions, if they are more favorable than the sum of solute-solute and solvent-solvent, then basically your solute will dissolve. Okay? Because you're going to want to go to more favorable interactions. If my solute-solute or my solvent-solvent interactions are much better and larger and more favorable than solute-solvent interactions, then there won't be a tendency to dissolve. And what we have to do is we have to take a look at the energetics of that. So, before we do that, London dispersion, as you know, those are your temporary dipole type of interactions. So these occur for all molecules. Dipole-dipole occurs for polar molecules. So if I have polar molecules and I have London dispersion and dipole-dipole. Hydrogen bonding is for a slightly positive hydrogen bonding to the lone pairs of oxygen, nitrogen, or fluorine. Okay, so if I have hydrogen bonding, most likely it'll be a polar bond. So I'm going to have hydrogen bonding, dipole-dipole, and London dispersion. When I've dissolved a ionic compound, so I have ions floating in solution, we talked about how if I have a polar solvent, I'll get those interactions there. And then ion, those are my ionic bonds. Okay, so let's take a look at some terms, and we'll also take a look at the energetics. Okay, so when you do go through the energetics, just be aware I will not be asking you to do another enthalpy table and Hess's law for it. Okay, so If we dissolve in water, okay, so you can call these interactions hydration. So just so you're aware, if you hear this term, okay, that's specific for water. Okay, so if you look, I look at my solute, okay, and it breaks up into N-solute particles, okay, so that's a delta H. So it takes some amount of energy to take a solute, a large crystal, and break them up into their individual components, okay, and that tells you a little bit about how much energy is involved in those solute interactions, okay. If I take a look at my solvent, I'm going to do the same. I'm going to take my solvent and I break them up into their individual solvent molecules. And let me get, if you don't mind me drawing a picture for you. So here are all my solutes, okay? And all I'm saying is to break them up into individual components. That's going to take energy, just like it took me some time and effort to redraw it separately. If I look at my solvent, okay, here's my solvent. This is like water. Remember we talked about water has hydrogen bonding, has dipole-dipole interactions, okay, and I break it up. So I'm looking just at the individual water particles. Then this is solvent, okay. Now, if I take a look, if I take my N solutes plus my M solvent, okay, and I make my solution. All right, remember we said that's mixing. Okay, so it takes some amount of energy to mix it. So here's what happens. When we're done here, to take my solute and to take my solvent, okay, to make a solution, it's going to be equal to the heat of solute plus the heat of solvent plus the energetics of mixing. Okay, so that's all we're saying. When we take these individual components, we mix it up. Okay, here's my N solute. Here's my M solvent. And all we're saying is now we're doing the mix. And this is my solution. Okay, so why is this? Why do I want to spend a moment to go over this? Because remember, if the total of this is a negative value, right, then that's going to be exothermic. All right, and that's why we're talking about if the solute energetics, if those interactions are strong and larger than this, then it's not going to want to go to N solute. Okay, if the solvent-solvent interactions are strong, then it doesn't want to be separated out. If we get a favorable mixing and these are weaker, then it's going to go to solution. Okay, so let's take a look at exothermic and endothermic formation of solutions. Okay, so let me just this is why we know it's going to be exothermic or endothermic. So if you look at magnesium sulfate plus water. Okay, and basically what I'm doing is I'm making a magnesium sulfate solution. This process, the mixing, is exothermic. Okay, and larger. All right. Then this H solution. Let me just say not mixing, but the solution. Sorry. Delta H solution is exothermic. Okay. Let's put it this way. So if we look at delta H mixing plus delta H solute plus delta H solvent, okay, what we find is this. This is very exothermic. So, and larger than solute and solvent interactions, and so it's exothermic when it dissolves. All right, let's give you an endothermic solution. Typically, if you look at ammonium nitrate, this is endothermic. So we know delta H solution is positive. So if we look at delta H of mixing plus delta H of solute plus delta H of solution, or solvent, excuse me, these two are positive, and the sum is greater than delta H mixing. And that's why this is an endothermic solvation process. So if you had like an instant cold pack, then when you break open the pack and you start dissolving ammonium nitrate in water, what happens is that it needs heat to dissolve, and so it's going to absorb the heat from your elbow, from your ankle. That's why it feels cold. It's because it's an endothermic solvation. Okay? So now that you know a little bit about making solutions, okay, so also be aware, right, solutions these are just mixing components. Okay, so in this case, when we look at something like nickel and hydrochloric acid, this is not like we're making okay, we're doing a reaction. All right, so just going back to your definitions, remember to in a solution, in a homogeneous mixture, you can get back your initial components through physical separation. If I do this, and I form nickel 2 chloride and hydrogen gas, I'm just doing a chemical reaction because I'm changing my substances. And they just want, your textbook talks about it because they just want you to be aware that while it looks like my nickel's dissolving, it's actually not. It's actually reacting and not just dissolving in water. Okay. But what we want to spend some time on actually is this. We need to spend time talking about saturated solutions, and solubility. Okay? So when we talk about a saturated solution, suppose here's my beaker, here's my solvent. Let's say my solvent right now is water. Okay? And let's do this. Let's add sodium chloride. Okay? If I add a tablespoon of sodium chloride and I stir it, okay, you're going to form a sodium chloride solution. Okay? Suppose I keep adding it. At some point, I add so much sodium chloride, okay, that while I have some in solution, I can stir all I want, but I'm going to have solid sodium chloride. It's not going to dissolve. Okay? Now, when that happens, you get this point where we call this, it's in equilibrium, dynamic equilibrium. Okay? And what that means is some of my sodium ion and chloride ion will combine and form a solid at the same rate as my solid goes back into the solution. Okay? So when I'm at the equilibrium, the question is, how much sodium chloride is dissolved in the water okay, at the specific temperature. Okay? And that amount, not here, not at the solid, but however much can actually go into solution and not come out. That is called my solubility. And the most typical units would be in grams per 100 milliliters, and you need to specify the temperature as well. Okay, why is that? Because solubility is temperature dependent. Okay? So, solubility describes how much solute is in my solvent at equilibrium. We say that this solution is saturated. So there are a couple of things that happen. You can say, oh, I can't learn anymore. My brain is saturated. What does that mean if you say that? My brain is saturated. What it means, let me just try to rewrite it so it's a little easier to see. When you say your brain is saturated, is that it's full and it can't hold anymore. Okay? That's what saturation means. Okay? If you are using a sponge, if you actually soak it in water and you lift up the sponge, and then after all the excess water comes up, Your sponge is what we'd say is saturated. It can't hold any more water. If I put in more water, it just drips off at the end. Okay? So that's what saturation is. What about this one? I added sodium chloride and it dissolved. If I continue to add sodium chloride, it'll continue to dissolve until I add in this excess, right? So if it still dissolves, this is called unsaturated. So the amount of sodium chloride, okay, that I have in solution is less than the amount here. Not only that, so you can still dissolve more solute. Okay, now let's go through an instance here. What happens if we did something like this? Suppose I have my solvent and I have my solute here, and then I heat it. Well, when I heat it, most times, it's not 100%, something like potassium chlorate actually decreases the solubility, but most times okay, at higher temperatures, the solute is more soluble. So I can actually add more solute. Okay, so let me give you, do I have a number for, oh, of course not. Let me look this up. Sucrose. All right, so suppose I have sugar in water. Okay, so it turns out, what's my solubility? Yeah, okay. Let me see if I can get your actual values. Okay. It turns out in, let's do this, at 20 degrees, mass fraction, solubility, grams. Okay, so at 20 degrees Celsius, you can dissolve about 200 grams of sugar. Okay? If I heat my water to about 100 degrees Celsius, so just about boiling, you can dissolve about 480 grams of sugar in water. Okay? So if I'm at 20 degrees and I put 480 grams in there, 280 grams is going to stay at the bottom. If I heat it to 100 degrees and I'm stirring it, then all 480 grams, will dissolve. Now what's interesting is this. Suppose I dissolve all 480 grams, okay? That's saturated. And then I cool my solution to 20 degrees. Okay? When you do that, if you're careful about not bumping it, you will have a solution that has 480 grams of sugar at 20 degrees. That's not possible. It's an unstable situation because that's way too much sugar in solution. This is called super saturated. Okay? And oftentimes what will happen when it's supersaturated is if I just put in one itty bitty crystal, all 280 grams that's in excess comes out. So if you add a crystal and you get a lot more solid than you added in, you are in a supersaturated situation, a supersaturated solution. If you were saturated and I put in one crystal, then that crystal will just fall to the bottom. You'll get exactly the same amount. If you were unsaturated, like at the 200 grams at 100 degrees, and I put in a crystal, it would just dissolve. So you can tell whether you are unsaturated, saturated, you're at the limit, or super saturated, you're too much. And if you ever do that and you feel the jar gets really hot. And that's because of all the energy that gets released, because now I'm going back into my equilibrium situation. This is not an equilibrium. Okay? And so it doesn't like to be in that type of situation. Okay, so let's talk about factors that affect solubility. Okay, let's talk about factors that affect solubility in solute. It'll be solute-solvent interactions. All right, we already talked about intermolecular attractions. So when we have a nonpolar solute and a nonpolar solvent, what's going to happen? Okay, so if it's nonpolar, then the only interactions between my solvent molecules are going to be London dispersion forces. If we look at my nonpolar solute, the only thing that holds them together will be London dispersion forces. So when I break apart the two and I insert it back in, I haven't really lost too much, because all that's holding them together again is going to be London dispersion forces. Because of that, we know nonpolar and nonpolar soluble. Okay? What happens if we have solute solvent, where what we have is my solvent is again like oil. Say it's nonpolar, but my solute is polar. Then you'd have a permanent dipole. Okay? So to hold the solute together, not only do I have London dispersion, okay, I could have hydrogen bonding. Or if it's an ionic compound, I could have ionic bonds, I have charge attractions. Okay, so if we go through and we try to dissolve my polar solute in my non-polar solvent, what happens is this. I have to break all of my hydrogen bonds, my polar dipole-dipole attractions. Okay? Break apart charge attractions if they're ionic compounds. And the only thing I get back here in return is London dispersion. And don't forget, since this is nonpolar, I'm trying to put charges in a nonpolar environment. So when it's nonpolar, polar for my solute, nonpolar, for my solvent, let's put this together, then what I get is it's insoluble. Okay? So far so good? Alright. So it's kind of like, let me give you some examples. Let me erase this. Give you some examples before we move on to the rest. Okay? So right now, let's see, draw it this way. Here's my solute. Here's my solvent. We have polar. Let's see. Let me just make this nice and pretty here. Non-polar. We have polar, non-polar. Okay? And so what we just talked about is that non-polar solute, non-polar solvent, yes, it's good. Okay? If we have a polar solute and a non-polar solvent, not good. Okay? So, an example here would be like mixing grease and oil. Right? Or you could say, how about oil paint and paint thinner? Okay. Your examples over here sugar and gasoline, or oil and water. Let me do the polar first. Water and oil. And just so you know, when you have two liquids, one is your solute, okay, and one is your solvent, they are said to be immiscible. They are not soluble. They are said to be miscible if they mix together. Okay? So just some new terms for you. Alright. Okay, so these are your examples. Polar, non-polar, sugar and gasoline, water and oil. If you have do oil painting and you need to clean your brush, you use paint thinner, you don't use water. That's because you want non-polar, non-polar. Or if you mix grease and oil, like if you're working on your car, your bike chain, and you need to grease it, you get all the old, black, dirty grease off, and then you have to wash your hands. And we usually use goop off, which is actually lanolin, which is sheep fat, to help clean off your hands first before you use hot water and lots of soap. Okay, let's go on to what happens if you have a non-polar solute and a polar solvent. Well, that's looking exactly the same like water and oil again, right? Here, if I have a non-polar solute, okay, and I have a polar solvent, then I'm breaking up all the interactions. Okay, so all the interactions that you're going to lose include your dipole-dipole, you're going to lose hydrogen bonding maybe, okay, and you're not going to gain them back, because instead what you have is you're going to just have interspersed a nonpolar solute. Okay? Which means that I have something in between, so I won't have those interactions. So it turns out polar solvent, nonpolar solute, again, won't mix. However, if I have a polar and polar, polar solvent, polar solute, let's change this. Then when I make my solution, those interactions, which I would have lost had I had a nonpolar solute, I can gain it back because now I can actually get these interactions back between my solute and my solvent. So it turns out if I have a polar solute and a polar solvent, based on our understanding of intermolecular attractions and interactions, we would find that this is still favorable. Which leads us, of course, to the statement that like dissolves like. Alright? So, it's like this. Let's do an analogy. You have a bear. Okay. In Alaska. In the Arctic Circle. Okay. And he jumps in the water. Alright? He's looking for a seal. And what happens is he disappears. Okay? There's another bear. Because he looks more like a guinea pig, but a guinea pig bear. Okay? And he jumps in the water. And this bear, he's in Wyoming. He jumps in the water, catches a trout, and he catches his fish and goes home. Okay? So the question is, why did this bear disappear? Okay, I'll tell you, but in the next slide. Okay. So let's go to the next slide first, and then we'll come back. Alright, so the next slide, okay, let's talk about the effects. Solubility. Okay. In this one, we're going to focus on gases. What happens is pressure affects solubility of gases. Okay, this page is over. Okay, so there's a law to it. It's called Henry's law. And the solubility of a gas, and this is going to be in moles per liter of solution, okay, is going to be equal to some constant times partial pressure of that gas. Okay? And that constant is gas specific. Alright? So, let's say for carbon dioxide. Okay? K is equal to 3.4 times 10 to the minus 2 moles. Oh, I don't like that minus 2. Minus 2 moles per liter atmosphere. Okay? So if I say your bottle, okay, has a partial pressure of CO2 equal to 2 atmospheres. What is the solubility? In molarity, in moles per liter. Okay, so when you apply this, all we have to do is follow Henry's law. So let me do the calculation first, and then I'll explain what's happening here. Okay, so if we do our calculation, you know that the solubility is going to be equal to 3.4 times 10 to the minus 2, and don't forget, this will be given. This is gas specific, and you have to look it up, okay? So we'll just make sure you don't have to memorize those. You'll be given those. And 2 atmospheres, okay? So my partial pressure, the solubility, okay, partial pressure is 2 atmospheres. The solubility of carbon dioxide is just going to be 6.8 times 10 to the minus 2 molar. Okay, now when we bottle carbon dioxide, we bottle it under higher pressures than that. And when we do, and we release that bottle, the pressure, the reason that you start seeing bubbles is that now we've dropped my partial pressure. And this solution is supersaturated, so it's going to release the gas in order to try to reach equilibrium. Now, why does pressure affect solubility? So let's take a look at it to understand the concept behind it. You can do a formula. You know how to figure out your numbers. Let's take a look. So here's my container. Here's my solvent, and I have some gas in there. And I have a bunch of gas. Here's a movable piston. Okay? When you increase the pressure, okay, so remember, if I increase the pressure, I can decrease the volume. So let me go ahead and show this to you. Here's my solvent. As I squeeze down and increase this pressure, all these gas particles here are going to be under immense pressure here. So what's a way to relieve that? Okay, and the way to relieve that is some of those particles will go into solution. So, 2, 3, 4. So, I'm basically, it's almost like physically just shoving it in there. So it's almost like if you've ever tried to fit all of your notes and your gym clothes and your books and your headset and everything else in your backpack. And when you initially start, you try not to squish anything in. And so you have a bunch of paperwork here in your books. You have stuff in your backpack. And you see, I have to fit everything in my backpack. So what you do is when you do it, after you try to straighten it and neaten it out, you kind of push everything in your backpack. You apply an immense amount of pressure just to squish everything into your backpack. And that's essentially what we're saying here. When we increase the pressure to increase solubility of gases. Okay? Now, why do we not talk about solids and liquids as much? It has an effect, but it's smaller because remember, when we look at solids and liquids, they're really closely together. Whereas gases, remember, those particles are far apart, and so they're very sensitive to pressure. Okay, so pressure affects the solubility of gases quite immensely, and we use that quite a bit. Okay, so what about temperature effects? We talked about a supersaturated solution previously. So in that sense, then we kind of have a pretty good idea. So for solid solutes, in most cases, solubility increases. Making rock candy, for example, making rock candy. We saw that sugar went from what? At 20 degrees, it was about 200 grams. It's 20 degrees Celsius. And at 100 degrees, it was about 480 grams. So you can see how significantly it increases. And same thing, sodium chloride increases, but it's a much slower incline. It's only like a couple grams. So for solid solutes, they mostly increase. There are some small ones that don't. What's mentioned in your textbook is your cerium sulfate. The solubility decreases, but everything else that they show in your table increases. So this is an unusual one. So basically at, let's say, 10 degrees, it was about 9.5 grams per 100 grams water. And then at 100 degrees Celsius, it drops down to about 2 grams, okay, per 100 grams of water. So, this is what you're normally going to see. It's very rare to see the other way, but you can, okay? So, I would say the rule of thumb is that in most cases, it's going to increase with temperature. And there you have it. Now, let's talk about temperature effects for gas solutes. When my temperature increases, my solubility decreases. This is for all gases. Okay? And if you think about it, when you have a gas, you see this is my water. Okay? The gas is a fairly non-polar solute. So gas doesn't like to dissolve in your solution. It will, but it doesn't like to. Now what happens is this. What's the only thing holding it? Most gases, if you look at it, are either non-polar or slightly polar. If they were very polar, there probably would be gases at room temperature. Okay? like slightly polar like ammonia, right? But the thing is, when you have it, okay, in solution, the thing that's holding your gas in your solvent is going to be your London dispersion forces. Okay? And here, some dipole. But what's more interesting is this. When you have your solution and your gases are interspersed in there, as I increase the temperature, what happens to my solvent molecules? My solvent molecules start moving more rapidly. So my solvent molecules increase their motion. Then on the molecular level, the small pockets that hold your gases are constantly changing, which allows your gas molecules to be able to migrate and diffuse through my solution and break my surface tension and leave. Okay, because surface tension also decreases as temperature increases. So my gases all will be able to escape more easily from solution. So the solubility goes down. So what are some of the examples? So some of the examples include this. If you ever compare let's say we'll take bubbling of CO2 out of, let's say, my diet soda. Okay, this is a cold soda. Okay, this is at basically 4 degrees Celsius, okay, in my refrigerator. And then I have a cold, not a cold soda, I have a soda. Let's say it's been sitting in the trunk of my car. So let's say it's about, not 20, that's too low. Let's say about 37 degrees Celsius. Okay, if you open this, which one's going to bubble over? Well, it turns out this one tends to bubble over very rapidly. Okay, cold one might bubble a little. Okay, but not nearly as much. Okay, and I say what's fun. Well, actually not for me, because usually I'm the recipient. So if my kids wanted to play a prank, they are old enough now not to do that, but when they were younger, they would have 2 cans of, for me, Diet Coke, and one would be cold and one would be warm. And so they would say, would you like a soda? I'd see them take out a cold soda, but they hand me the warm one, and I open it, and I end up getting soda all over me because it bubbles over really rapidly. Whereas when we get a cold drink, we open it carefully, but the rapidness of it isn't there. And the reason is, at 37 degrees Celsius, all of that CO2, there's a lot more carbon dioxide that's just pushing itself out of solution here than it is here. Okay, so before we move on to your next topic, then I'll tell you what happened to the bear. The bear in the Arctic Circle, what kind of bear was it? It was a polar bear. The bear in Wyoming is a brown bear. What do you know about water? Seawater, plain water, it's a polar solvent. Okay, so we know like dissolves like. So, what happened to the brown bear? Nothing. To the polar bear, since it's polar and water is polar, polar bear dissolves. And there you go. And if I ruined the joke for you, I apologize. It wasn't the best joke, but I love it anyway. Okay, let's move on to our next subject.